And now in this lecture we'll find out the length of line segment X using two different methods. In the drawing we have a semicircle. You know that chord AP equals to line segment PC equals to X, and X is the line segment that we are looking for in this question. We have to find out the value of X. So the length of AP is equals to the length of PC. In addition, we know that AB equals to 10 units in its length. AB is actually the diameter of the semicircle that is equals to 10 units in its length. BC equals to 6 units in its length. Again, our task is to find out the length of line segment AP. This is equal to X. So first of all, we will define the center of this semicircle. This point is point O. The diameter of this semicircle is AB. The diameter over 2 is equal to the radius. The diameter AB is 10. Over 2 is 5. So if we found out that the radius of this semicircle is equal to 5 units in its length. OA is the radius of this semicircle that is equal to 5 units in its length. OB is also the radius that is equal to 5. In the next step, we join point O. Point O is the center of the circle. Point O and point P together by side 9. PO is of course the radius of this semicircle that is equal to 5. So here, by doing this construction, you can do the associated triangle, triangle AOP. Why triangle AOP is an associated triangle? Because of the fact that AU equals to PO. Those two sides are equal to each other, therefore triangle AOP is an associated triangle. And we know that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be equal to each other because they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle APO, this is the right triangle APO. This angle equals to alpha, this angle also equals to alpha. Therefore, this first angle must be equal to 180 degrees minus 2 alpha. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, the big triangle, triangle APC, is an associated triangle because AP equals to PC according to what is given in this equation. So in front of those two equal sides, we have those two angles that must be equal to each other according to the rule that in front of equal sides in the triangle there are equal angles. But so those two angles are equal to each other, but this angle equals to alpha. Therefore, this angle must be also equal to alpha. So, in the next step, I'll copy the big associated triangle, triangle APC, and the small associated triangle, triangle POA in a new page, and we'll prove that the big associated triangle, triangle APC is similar to the small associated triangle, triangle APO, according to angle similarity rule. In the associated triangle, triangle APC, this angle equals to alpha, this angle also equals to alpha. Therefore, this third missing angle must be equal to 180 degrees minus 2 alpha. According to the theorem, the sum of the angles in a triangle is equal to 180 degrees. Side PC on the big isosceles triangle APC equals to x, and side AP also equals to x. What is the length of side AC of the big triangle APC? Side AC in total equals to AB plus BC. So AC in total equals to AB, that is 10, plus BC, that is 6. So in total, AC equals to 16 units in its length. Side AC equals to 16 units in its length. AC equals to 16. Actually, side AP is a common side that belongs to both triangles. Side AP belongs to the small isosceles triangle AOP, and side AP belongs also to the big isosceles triangle APC. So actually, those are the two isosceles triangles that are coming from the original domain. This is the isosceles triangle, the big isosceles triangle ACP, and this is the small isosceles triangle AOP. So why those two triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are also equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. So if we prove that all the three angles of the big isosceles triangle APC are correspondingly equal to all the three angles of this small isosceles triangle APO, and therefore those two isosceles triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big isosceles triangle APC is similar, this is the sign of similar, to the small isosceles triangle AOP according to angle similarity rule. And from the fact that those two isosceles triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AC of the big associated triangle APC over side AP of the small associated triangle APO. So side AC over side AP is equal to side AP of the big associated triangle ACP over side PO of the small associated triangle APO. So in total, we found out that AC over AP equals to AP over PO. AC is 16 over AP. AP is the line segment that we are looking for in this question. It is equals to X, and it is equals to AP, it is again X, because of the fact that AP is a common side that belongs to both triangles. AP belongs to the small associated triangle APO, and AP also belongs to the big associated triangle APC. So it is AP over PO. PO equals to 5 units in its length. Actually it is the radius of the semicircle. So in total we actually found out that 16 over X equals to X over 5. So here we will cross multiply this equation, and we get that X squared equals to 16 times 5. X squared equals to 16 times 5. Here we take a root out of this equation, and finally we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we found out that the length of line segment AP is equals to X. It is equals to either 4 times square root of 5 units in its length, or in terms of numbers it is equals to 8.94 units. If it again, we found out that according to the first method, the length of this line segment AP is equals to X. It is equal to either 4 times square root of 5 units, or in terms of numbers, the length of this side AP is equals to X is equal to 8.94 units. So we finish with the first method. In the next step, I will present to you how to find out the length of this line segment AP is equals to X according to the second method. In the second method, we will use the rule that in any associated triangle, the perpendicular to the base bisects the base. Okay? And again, we use the rule that in any associated triangle, the perpendicular to the base bisects the base. So, in the drawing we have triangle APC. The big triangle APC is an associated triangle. Why the big triangle APC is an associated triangle? Because AP equals to PC. AC is of course the base of the associated triangle APC. But first of all, we define the center of this circle as point O. The radius is 5 because it is the diameter 10 over 2 is 5. So the radius of the semicircle R equals to 5. Again, we use the rule that in any associated triangle, the perpendicular to the base is AC, bisects the base. So we will draw the perpendicular to the base in this associated triangle APC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AC. This point is point M. And but before that, AC in total it is 10 plus 6, that is 16. AC in total So the base AC is 16 units is equal to 16 units in its length, because it is 10 plus 6. AC, the base AC equals to 16 units in its length. And according to the rule that I mentioned, the perpendicular PM to the base AC bisect the base AC. That is to say, each half will be equal to AC over 2. AC is 16, therefore PM bisect the base AC. Therefore the first half must be equal to AC over 2, that is 16 over 2, that is 8. So AM equals to 8. AM equals to 8 units in its length, according to the rules I mentioned. We join points P and O together by a straight line. PO is of course the radius of the circle, because point O is the center of the circle, point P is the point on the circle itself, therefore PO is the radius of this semicircle, is equals to 5 units in its length. So PO equals to 5. PO equals to 5, it is the radius of the semicircle. What is the length of line segment OM? OM, so AO is of course also the radius of the semicircle, that is equal to 5. So what is the length of line segment OM? From the drawing it is very easy to see that OM equals to AM minus AO. Again, OM equals to AM minus AO. So I write it down. AM, again OM is equal to AM minus AO. So OM equals to AM. AM is 8 minus AO. AO is the radius, that is 5. So in total, OM equals to 8 minus 5, that is 3. OM equals to 3. OM equals to 3 units in its length. So in the small right triangle PMO, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the small right triangle POM, PO square equals to OM square plus MO square. So write it down. In the right small triangle PMO, by PT is the relation from Pythagoras theorem. The square of the hypotenuse is PO square is equal to PM square plus OM square. Repeat again. In the right small triangle PMO, according to the Pythagoras theorem, PO square equals to PM square plus OM square. PO is 5, therefore PO square is 5 squared, that is 25. And it is equals to PM square. PM is the missing side, so we leave it as it is. So it is PM square plus OM square. OM is 3, therefore OM square is 3 squared, that is 9. So in total, we actually found out that 25 equals to PM square plus 9. Here we will subtract 9 from this equation, and we get that PM square is equal to 25 minus 9 is 16. So PM square equals to 16. We'll take out all of this equation, and finally we get that PM equals to the square root of 16, that is 4. So PM equals to 4 units in its length. This is PM, that equals to 4 units. So in the next step, we'll implement the Pythagoras theorem in the big right triangle PMA. So copy the big right triangle PMA in the new page, and we'll implement on it the Pythagoras theorem. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle PMA that I copied from the original drawing. This right triangle PMA, AP equals to x, that is the line segment that we are looking for in this question. The hypotenuse AP equals to x units in this line, PM is 4, and AM is 8. So according to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, must be equal to PM squared plus AM squared. AP is x, therefore AP squared is x squared, and it is equal to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total we should find out that x squared equals to 16 plus 64, that is 80. X squared equals to 80. 80 is 16 times 5, so we substitute 80 by 16 times 5. So x squared equals to 16 times 5. Here we take a root out of this equation, and we get that x equals to the square root of 16 times 5. The square root of 16 is 4. Inside the root we left only with 5. So in total we should find out that x equals to either 4 times square root of 5 in units in its length, or in terms of numbers it is equal to 8.94 units in its length. So we arrived to the same question, to the same result as we arrived in the first method. In the first method we also arrived to the result that x equals to either 4 times square root of 5 units or 8.94, exactly as in the second method. Okay, so we finish with the second method. In the next step, I will summarize the lecture. We'll start with the first method, of course. So, in this lecture, our task is to find out the length of line segment AP that is equals to x. So in the drawing, we have a semicircle. We know that the diameter of the semicircle AB equals to 10 units in its length. This is line segment BC that is equals to 6 units in its length. AP equals to PC equals to x, and our task is to find out the length of line segment AP that is equals to x. We have to find out the value of x. So the diameter AB of this semicircle is 10, therefore the radius must be equal to half of it. That is to say, the radius must be equal to 10 over 2, that is 5. So the radius of this circle is 5. So OA is the radius of the semicircle that is 5, OB is also the radius that is 5. We join points P and O together by a straight line. PO is of course the radius of the semicircle that is 5. So here, by doing all those construction created here, the small associated triangle, triangle POA. Why triangle POA is an associated triangle? Because of the fact that OP equals to OA equals to 5. So we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be also equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. Likewise, in the associated triangle, triangle APC, why triangle APC is an associated triangle? Because side AP equals to side PC. So in front of those two equal sides, we have those two angles that must be also equal to each other, because they are located in front of those two equal sides. But this angle is alpha. We only found out that this angle equals to alpha. Therefore, this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. So in the next step, I copied the associated small triangle, triangle POA, and the big associated triangle, triangle APC in the new page, and we proved that those two associated triangles are similar to each other according to angle similarity rule. So actually, those are the two associated triangles that are copied from the original drawing. This is the big associated triangle, triangle APC, and this is the small associated triangle, triangle AOP. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So if you found out that all the three angles in this big associated triangle, triangle APC are correspondingly equal to all the three angles of this small associated triangle, triangle APO. And therefore those two associated triangles are similar to each other according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AC of this associated triangle, triangle APC, over side AP of this small associated triangle, triangle APO, is equal to side AP. AP is the common side that belongs to both triangles. Is equal to side AP of this big associated triangle, triangle APC, over side PO of this small associated triangle, triangle APO. Okay, AC over AP equals to AP over PO. AC is 16, AP is X, that is the line segment that we are looking for. Again, AP is X, and PO is 5, that is the radius of the semicircle. So in total, we actually found out that 6 over X equals to X over 5. Here we course multiplied this equation, and finally found out that X times X is X squared, of course, so X squared equals to 16 times 5. Here we took out the root out of this equation, and finally found out that X equals to the square root of 16 times square root of 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we found out that X equals to 4 times square root of 5. In terms of numbers, X equals to 8.94 units. Repeat again, the length of this line segment AP is equals to X. It is equal to either 4 times square root of 5 units in its length, or in terms of numbers, X equals to 8.94 units. So we finished with the first method. In the next step, I presented to you how to find out the length of this line segment AP that is equals to X according to the second method. In the second method, we use the rule that says that in any associated triangle, the perpendicular to the base bisect the base. But again, we use the rule that in any associated triangle, the perpendicular to the base bisect the base. So this is the associated triangle, triangle APC, because AP equals to PC. This is an associated triangle, so in this associated triangle, triangle APC, AC is the base. So from point P, we draw perpendicular to the base AC. And according to the rule I mentioned, the perpendicular PM to the base AC bisect the base AC. The base AC is totally 16, so it bisects the base, so each half must be equal to 16 over 2, that is 8. So AM is 8, and MC is also 8. So AM equals to 8 units in itself. We join points P and O together by side line PO is the radius of the semicircle, that is 5. And here we have OA is also 5 because it is the radius of the semicircle. AM is 8 according to the rule that I mentioned. So OM will be equal to AM minus AO. Again, OM equals to AM minus AO. So OM equals to AM, that is 8, minus AO, that is 5. This is the radius of the semicircle, that is 5. So in total, OM equals to 8 minus 5, that is 3. So OM, this small line segment, OM equals to 3 units in itself. 8 minus 5 is 3. So OM equals to 3. So in the next step, we implemented the Pythagoras theorem on this right small triangle PMO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right small triangle PMO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. Again, PO squared equals to PM squared plus MO squared. So in the in the small right triangle PMO, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equals to PM squared. PM is the emission side, so we move it to 60. So it is PM squared plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we actually found out that 25 equals to PM squared plus 9. Here we subtracted 9 from this equation and finally found out that PM squared equals to 25 minus 9 is 16. So PM squared equals to 16. We took out of this equation and finally found out that PM equals to the square root of 16, that is 4. So limits inside PM equals to 4 units in its length. In the next step, implemented the Pythagoras theorem with a big right triangle APM. So copy this big right triangle APM in a new page and implemented the Pythagoras theorem on this right triangle APM. So this is right triangle APM, that is copied from the original drawing. AP equals to X, that is the 9 segment that we are looking for in this question. AP is the hypotenuse, PM equals to 4, and AM equals to 8. So according to the Pythagoras theorem, in this right triangle APM, here by PT is the expression for Pythagoras theorem. AP squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. AP squared equals to PM squared plus AM squared. Okay. AP is X, therefore AP squared is X squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total we found out that X squared equals to 16 plus 64. 16 plus 64 is 80, so X squared equals to 80. Here we took out of this equation and finally found out that X equals to, actually we substituted 80 by 16 times 5. So X squared equals to 16 times 5. Here we took out of this equation and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we actually found out that X AP is equals to X, it is equals to either 4 times square root of 5 units in its length, or in terms of numbers, X equals to 8.94 units. Okay? Thank you very much.